So we can recap the yesterday's session. We have seen so many steps in Autodoc, the major steps in Autodoc, and I think you also received a kind of a tutorial to how to go for docking. But we have also discussed before going for hands-on experience in Autodoc, we also discussed something related to uh, the theory behind molecular docking. Okay, so we have also seen some tools for docking ligand protein and docking protein. Okay, this is the generally we follow for ligand protein or protein protein. So we'll be discussing about that now. So give me some two examples of the tools. Example for tools of ligand receptor docking. Tools of ligand receptor docking. If you want to dock a small molecule with a protein target, what are the tools we can use? What are the freewares we can use? Good from MGL tools or nothing but Autodoc. Also, we have discussed in Autodoc we have four versions, isn't it? Good.
Glide Maestro.
Maestro, very good. Croydon Maestro, isn't it? Okay. And then what else? UCSF Chimera,
CD
good.
Doc. Gold Access.
Chimera Docker. Chimera is a kind of a visualizer. Hmm. UCSF, you have
CD Doc
Doc.
is there.
Yes, you're right. CD Docker is a different software. Good. And UCSF, you have a
Pyrex is
doc.
also for virtual screening and docking. Pyrex and Discovery Studio.
Good. Pyrex, but Pyrex is a virtual screening. That is, you dock multiple ligands with the receptor simultaneously. Okay, but if I ask you simply ligand receptor, not if I'm not asking up to the virtual screening, then you can mention about Autodoc Vina, Autodoc 4.0, covalent Autodoc. So these are the tools generally we dock single ligand with a single target receptor. But in Scroid, there is a package. Like if I ask you to how, what is the software used for drawing the graphs, we generally go for MS Excel, isn't it? Microsoft Office Excel. We
Origin
got
has also there, sir. Origin Pro.
good, madam. But first, I can clear the doubts of Unikrishnan. The Unikrishnan has mentioned Scroid Inger. The Scroid Inger is a package. Okay. If I ask you what is the software used for drawing the Excel sheets, I can tell MS Office Excel is generally used. You can't tell MS Office is used for drawing the Excel sheets because in Office you have Word, Excel, PowerPoint, Access, and other softwares also, isn't it? Explorer, etc. So many softwares are there, but likewise, Scroidinger is a package. If you want to talk a ligand receptor, you can tell like Scroidinger Gold for protein docking and for Scroidinger Glide, GLID. This is for ligand receptor docking. Okay. So we have different tools in the Scroidinger itself for ligand protein and protein layer. I have to check that. We have to mention about gold, isn't it? This gold is for protein docking. Good. And now we can go for the ICM doc. Good. But of course, the Scroidinger, ICM doc, all are commercial softwares. And of course, Madam is also mentioning few more softwares. Just I didn't okay, so there are also many softwares, hundreds of softwares are there. Okay, so I know now up to hundreds, but even 500 softwares are there in the internet to download or to work in online. Good. Now, can we go for tools for examples for protein to protein docking? Now we have mentioned for the ligand receptor. Now, can we go because we can't match for ligand receptor and protein docking. We use entirely different tools. Not only in packages, even the online tools what we use is entirely different for protein docking when compared to ligand receptor, ligand protein docking. Now, can I anticipate answers from the participants? What are the examples you can? What are the tools? I am telling you the tools used for protein docking. Of course, we also have databases, protein docking, 3D docsert. Okay. What else? Class Pro. Good. Class Pro is a talk, Hex talk, Hadoc. Good, good. So I think you're also mentioning now about a list of tools for protein talking. Oh, good. I think teacher
3D
also
doc,
what,
3D
madam?
doc.
3D docking. Good, good. Okay, now I think many participants are providing more answers on this. I need this kind of an interaction in the subsequent sessions. Let me go to today's session on molecular docking analysis. You remember yesterday we have docked in a folder. We have used the files for docking in a folder called demo1, where I used indinavir as a ligand. There is a HIV drug. I just talked with a kind of a protease complex, and I checked a kind of the energy. We come up with the best two poses. The first pose given some negative maximum energy. Okay, now okay, if you want to see the kind of that result, the energy result, what we generated on yesterday. Okay, you have to open the file and so there is one file called .dlg. This is a log file, but there is another file called DPF, docking parameters file. So the docking log file, docking parameter file. Now I can open each and every file. First I am opening the parameter file. Docking parameter file is .dpf. I increase the view. Okay, now I can show you. In docking parameter, whatever default parameters they have fixed, all this information are available here. See, whatever you talk, we keep some parameters as default before docking, isn't it? If you want to find these parameters, you can find from here. So initially, before talking, we just had only 5 files. Only the what five files we had? We had Indinavir, that is a ligand 3D structure, protease, 3D structure of a protein. We had Autodoc 4 tutorial. This is a third file, and Autodoc 4.exe and Autogrid 4.exe. Totally, we had 5 files. But now you got almost multiple intermediate files. Okay, you got in the form of .map, .dlg, .dpf. I think you might have seen in the steps. Okay, in intermediate steps, you have generated GLG, then you have generated GAPF. Okay, then you have used it for running the AutoGrid. Similarly, even for before running the AutoDock, you have generated these files. But even the map files are generated obviously, and this is the final file we have created. That is before closing the AutoDock window, we got a ligand protein complex.pdb file. Okay, so this is the file we will be using for analysis. But before going for analysis, if you want to get an energy information instead of DPF, better go for .dlg. Okay, these two intermediate files give you what exactly we have used and what exactly we got. Now in DPF, you will be seeing the output. So let me show you the coordinates, output of the ligand protein docking, that is uh, Indinavir protease. Okay, I'm just dragging down. So first I can see and then I can show you. This is for second pose. This is for first pose. See, actually, if you see here, I just zoom in and show you. Yeah, the estimated free energy of binding, what we got is minus 8.68 kilocalorie per mole. So this is the energy we got for the best dog pose. Okay, actually, in number of genetic algorithm runs, I provided two. I provided the value like 2, so I got only 2 best dog poses. But if you go feed as 10 in default, you get 10 best dog poses. Participants, you should remember that you should not select the pose 2, which is given the maximum negative maximum like minus 8.68, even though you got the least maximum for the second pose. And if you see the first pose, you got a lesser value than this. Okay, you have generated two poses. You see the first pose value is just minus 6.78 kilocalorie per mole. So out of two poses, one is minus 8 point something and the other is minus 6.78. If you compare this pose 1 and pose 2 is best. No doubt in that. But even, while generating the complex file, while generating this kind of a complex file, internal protease complex, if you have selected the second pose, that is minus 8 point something in default, And if you try to go create a complex, then only in the second pose it might have created a complex. It has uh, you have created a complex with only the second pose and not the first pose if you select the second pose. If you have selected this pose and create a complex, then you create a complex only for with the first pose alone. You got it? So you can create two different poses. So obviously, even the amino acids, whatever you, the binding set amino acids, whatever you generate, or two set of amino acids. Here you get a different kind of an amino acids if you go for analysis, and if you generate for this pose, okay, you'll be getting a different set of amino acids. So why I'm providing you this information? Because if you go for the molecular docking, if you know the binding sites, okay, you have to see your ligand is binding exactly with the binding sites or not. Even though the pose 2 energy is best, but if you see this pose 1, if you get a desired binding site amino acids, then you have to select only pose 1. You can't go for pose 2. The first dominant characteristics, what we consider in molecular docking analysis, is binding site amino acids. Okay, the second only is the energy. But remember, whatever energy you generated from different poses, the energy should be -6 and below. Just because even this pose energy is -6 and below, even you can consider this as a significant docking. I think one participant has uh, unmute. So you just kindly mute participants. So some kind of disturbance I can't have. Okay. Okay. Now we can see here. Then even in the second post, you got -6.78. So it means that okay, even this post is also significant. Got it? But only thing which is decided to select is based on the during the analysis, during the docking analysis. Only after creating the complex only you go and go for docking analysis. During the analysis, if you get a binding site for a particular post, you select that post and you show that the energy and you tell these are the binding site amino acids you get. The reason why here is a protein macromolecule is of large size. Your small molecule can bind in multiple binding sites of a protein. Okay, so you can't tell that even if you get a negative maximum energy for pose 2, the ligand has bound with the binding sites, might you have more hydrogen bond interactions. So only you are getting negative maximum energy. But here you have in the less hydrogen bond interactions, but you can find your ligand is binding with the exact binding sites. Then you understand. So even selection of a desired pose is based on first binding site amino acids, then only whether the energy is significant or not. Okay, now let me take you to the demo one folder. Here now I already created a complex on yesterday. Remember up to the last step. Okay, now I'm not going to analyze through the third molecular viewer, but I use BioViewer Discovery Studio. This is a freeware. Anyone can download and install this software, and it's very easier for you to practice. User friendly, more user friendly. So I suggest you to use this when compared to Python molecular viewer, where you also have to depend on commands. Okay, you should know about commands to use the Python molecular viewer. Here there is no use, just drag and drop and use the mouse, click the mouse over. All these events work perfectly. Okay, the mouse, you can handle everything using the mouse. Now let me take you to the talking analysis. The first step is to go to the scripts. Okay, selection, select ligands. Okay, before going to this, I can also give you one more information. I'm not getting any details about this protein. Of course, we have ligand talk with the protein. Initially, on yesterday when I showed a protein was a separate, a protein I viewed in a separate visualizer, and ligand I shown in a different visualizer. I mean a different window. Now, if you see this, all these two are found in a single window. It means that you are already fine. A ligand is talked with the receptor. But if you want to get more information, even up to the atoms, you will click view hierarchy. If you click view hierarchy, okay, you can find A chain. So you find the amino acid from proline to the phenylalanine A chain. This is for A chain. Okay. And if you click here in the chain, you get MK1902. It means that if you select this MK1902, only the ligand is getting selected. Okay, and heteroatoms, if you have removed any water molecules, you won't find heteroatoms. So I didn't find anything. But if you use the water molecules and use for docking, even you can find water molecules selected if you select the heteroatom. Now you can also find some more information on this. Okay, now first objective is to find the binding site amino acids. So for that, okay, after clicking view hierarchy, go to the scripts, selection, select ligands. So you have only one ligand that is got selected now. In case of metal binding proteins, even the metal is going to be get selected. Then you have to deselect it if you, because there is no need whether this metal is binding with a kind of hydrogen bonds or not. Only thing is that if you use a drug, only the drug alone is considered. So deselect it. But here in our case, we have just a protein we have, and a ligand is nothing but a drug. So I'm just whatever selected is okay for us. Select atoms within 4 angstrom. So it means that you are going to select the binding sites within 4 angstrom. You know, the protein, whatever we have taken, okay, that is a protease. If you want to study about the protein, okay, just clicking the protease, open with Windows site. You can see, I think I don't have much information on that because it's a modeled structure. So we don't have a header and title. But if you have downloaded any protein, for example, I also have one more protein called 4q3i. So now I'm going to open in Windows site. Just for an example, I'm showing you. So each and every protein, okay, is going to have a PDB ID and also going to have a resolution. This is what I want to mean. The resolution of a protein, if a resolution of a protein is less than 2 angstrom, then the protein structure what you're using is a high resolution protein. Got it? If it is 2 angstrom to 4 angstrom, then it is a medium resolution protein. If it is, if the protein structure is you find above 4 angstrom, then it is in low resolution. Generally, we anticipate to get a high resolution protein. For example, if you are working for a particular protein, and if you also have a protein of 1.6 angstrom, I suggest you to use 1.6 angstrom, then 1.86, because you're going with high resolution. That is, you know about dots per inch, isn't it? Even in your mobile, you have some 54 megapixel. Initially, we had 8 megapixel. If you had a kind of a 8 megapixel, okay, and compared to 54, is very we have the dots per inch. We have very less dots per inch, so the quality is not good. If you go for more megapixel camera, then you find more dots per inch, and obviously the quality is more fine. Similarly, here you have to find the lowest value. So we have to check this resolution also. Okay, if you see this resolution, they are telling like 1.86 angstrom is the distance between one atom to the another atom in an amino acid. Okay, generally, actually, if you see the kind of, the atom distance is generally 1 angstrom, but whatever structure they have modeled, okay, the resolution is of model, whatever they generated, whatever structure they have generated through X-ray crystallography or NMR, okay, the resolution is just 1.86 angstrom. But according to the general visualizer, okay, it can be Python molecular viewer, RAS small, Swiss viewer, Discovery Studio visualizer, generally uses uh, the atom as a particle, and which is going to have a 1 angstrom level. So here for determining the nearest binding set amino acids, we are using 4 times, so 4 angstrom. So I'm going to select atoms within 4 angstrom. Now this process is completed. Initially I selected ligand. Now select atoms within 4 angstrom to determine the neighboring binding site amino acids of a ligand. And now I go for the ligand interactions, show ligand binding site atoms. This is the next step. Ligand interaction, show ligand binding set atoms. Now we got a kind of hydrogen bond monitor. So if you see the hydrogen bond monitor, okay, so you can able to find so many binding site amino acids. The binding sites can be selected, okay, based on the ligand. If you see the ligand MK1902, okay, so the MK1902 binding site amino acid is 30980. Okay, so MK1902, okay, you have oxygen 4, is interacting with the hydrogen of gamma chain of A chain of 30980. Okay, so this is one such binding site amino acid, that is 30980 is the binding site amino acid present in A chain. And the second binding site what we can find here is again 30980 but in a different positions, the different ligand position and different position of an amino acid. So of course 30980 is one of the binding site amino acid, no doubt in that. You have it two different contacts, that's it. And I don't find any other amino acids. So for this example, we got only one, and also I got one more here, lysine 48. So 3980 is one binding site amino acid, glycine 48 is the second binding site amino acid. Now, whatever you got 48 and 80, this you can able to first initially you got so many nearest binding site amino acids, you first deselect it. If you want a getter view, you first deselect it, and now you have to select 48. And what is the other? 80, isn't it? That also I have selected now. Only these two binding sites alone I have selected. Now you can able to see this binding sites is sharing a hydrogen bond in dotted green lines. Okay, whether you can able to see, but this kind of interaction, okay, is not clear. Okay, if you want to show it in publication, this won't looks better, isn't it? So what I'm going to do here is first initially I'm going to label this. I'm going to label. No, I'm not getting it perfectly. I'm going to first I cancel it. I first select the 30980 and glycine. Now I right click here and change the display style. In display style, I'm going to keep that particular amino acids in ball and stick. Click apply. Okay. Before clicking OK, you can go to the graphics. The background color generally in a journal paper is white. So I'm keeping it in white. So I got a white background. Okay, so label is on, of course. Yeah, but the font size is very small. I increase the font size something like 26. Click it, click OK. Now you got even a kind of, but the labeling I suggest to use um, for instead of hydrogen bond, go for amino acid. Okay, and in amino acid you can go for 3-letter ID and insertion code. Amino acid 3-letter ID insertion code. You can use this. If you want to change the color, you can change the desired color whatever you want. I just changing it to the maroon color. Okay, amino acid 3-letter ID and insertion code. Yes, I got the amino acid. Click OK. Now you can able to find an amino acid, or if you want to change the color, you can change the color however you want. So this is present in label side. Okay, so the initial color itself is, if you feel okay, you can use that. Or okay, I just changed the color now. Okay, so you have this kind of binding site amino acid. Now you should also show the entire protein, then it looks fine. So I select the entire protein. You got this kind of a ribbon. You can able to find the entire protein in solid ribbon, and this ligand alone. This ligand alone is in stick model, and the binding site amino acids are in ball and stick model. Okay, so this is how we can able to show. So there are different poses. There are different ways of showing the result. If you want to show this in the form of surface model, you can click surface set. Okay, so keep the default parameters like soft solid and click OK. See here, in the surface model when I did, I don't find my ligand. My ligand is fully buried inside. It means that the ligand is binding in the hydrophobic binding sites. The ligand is not binding somewhere in the surface of the protein, but it is binding inside, isn't it? So just because we find a buried ligand, so we can tell our ligand is binding in the hydrophobic site. So you have plenty of results. One result, what I showed you, is the 3D structure of interaction of the ligand with the receptor. Protein alone I kept in solid ribbon, and ligand I kept in stick model. Binding site amino acid I shown in ball and stick. Now I'm showing a surface model where I also telling like ligand is binding in the hydrophobic site. Okay, so this is also one result. And the next result, what I showed is here the binding site amino acids. 30980 is the binding site amino acid. Of course, our ligand of O4 position is interacting with the hydrogen of gamma position 1 in 30980 amino acid of a chain. Similarly, glycine for 48 of O oxygen atom is interacting with the nitrogen atom of the ligand. Okay, so likewise, I can able to show this kind of information. So other than this, what else we can show? We can also show the so before I think the control Z, I can go back. So after going for the interactions, if you go for control Z, you get detail. Okay, so if you want to get a 2D structure, okay, before going for 3D interactions, you can also find this option is highlighted. Click show 2D structure. Now you can see your ligand is interacting. Okay, so this information you can able to see. If you want to change even the display style, okay, even you can change this. Can change the display style. I think still you can. The binding set amino acids are not shown, isn't it? So I do one thing, I can close and I can open once again and I can show you the 2D interactions. So 3D interactions I showed you, I have demonstrated how to make it. For 2D interactions, simply open the complex, okay, and then you have to, go for view interactions, click show 2D diagram. So an excellent 2D diagram, you have generated excellent 2D diagram, okay. Your ligand is here. If you want to find your ligand, click display ligand. Okay, or better, you can use the view hierarchy so that you can select that alone. View hierarchy. I'm going to select the ligand alone by clicking the chain. Okay, this alone is getting selected in both 3D and 2D. Now click display style. Okay, if you want to have even the distance of contacting distance, you can click show distance. And if you want to have the ligand in the form of ball and stick or stick, whatever you want. If you want in the form of a stick, you keep it in stick. Okay. And even if you want to change parameters, you can change parameters or simply click apply, click OK. Now getting outside, see your ligand and stick model is interacting with the binding site amino acids and also you can find the bond length. Okay. So in 2D structure, you have to get a snapshot of both this binding site information, the glycine 448. You can see the binding site. The hydrogen interactions are found in glycine A48 and also in 30980. Okay. So whatever earlier I have explained you, like going to the scripts, find the ligand and find the atoms within 4 angstrom and show the binding site interactions. All these things are a data. Here also you get the similar data in the 2D interactions. Okay, but you don't know what atom of 380 is interacting with it, isn't it? So then you have to go to whatever steps earlier I explained. Okay, so this is how we can go for molecular docking analysis of ligand receptor complex. Okay, yeah, do you understand? I think we didn't ask any queries. So let me go to the next chapter, that is on MATLAB. You remember, so before I can ask you, like, do you have any doubts in the molecular docking analysis? Is it clear? Yes or no? Can I anticipate answers from your side?
Sir, what is the
Well,
difference between Discovery Studio and Discovery Studio Client?
Discovery Studio if you purchase a
Yes.
discovery studio in academic, okay, in your college, or if you're working in industry, if you purchase this kind of a software, okay, they provide you for initially a discovery studio server version, okay, and if you want to work for 5 clients, okay, then the server, whatever they install, they connect the server with the clients. And whatever we are practicing in our home, whatever I just explaining you, is a Discovery Studio visualizer. This visualizer software is commonly observed in both clients as well as server. But in server,
Sir,
you
is can we perform docking with this visualizer?
how come this software expenses around 15 lakhs to 25 lakhs based on what bundles you want in your package. Okay, so this comes around. This is an expensive one. You have to contact the BioVia vendor and you have to check. Okay, this is not less than 15 lakhs, I believe. So how come you can do all the docking? Only thing is that you can analyze the docking results. This is alone is possible. Okay, any other doubts you have? Which is the best free tool for docking that can be used? I use only Autodock. Okay, so as academicians, or students, researchers, we can go for Autodock. That I can suggest you that as the best free tool. But if you're working in well-reputed institutions and if they have a commercial software, it's better work on the commercial softwares. Go for Scrodinger, go for Discovery Studio, go for Triple 7, go for whatever softwares you have. Okay. What is the difference between Autodock and Autodock Winner? You just search on internet. There are a lot of blogs are there. Okay. Autodock, I told you 4 versions are there. One such version is the Autodock Winner. Okay. Only thing is that you have to search more information. Okay. So you have JIT, I understand. But I think instead of spending time on Autodock, can I go for the next concept MATLAB? I don't think many of them have awareness on MATLAB because even MATLAB is a commercial one. Okay, if only if you have the MATLAB, then only you can able to understand how to work with it. So obviously, in my institution we have a MATLAB. So each and every student also have a MATLAB. So those who have an institutional email ID, so they can access this kind of a MATLAB software. So let me take you to this session, MATLAB. So MATLAB. So just because I'm going to use MATLAB, I'm going to close this visualizer. Don't save the changes unless you want. Okay, I just closed it. Now I'm going to open you the MATLAB. So before going to the MATLAB, I can show you some slides. Okay, I just about the MATLAB. Start with MATLAB Symbology. Yes, good. Now I'm explaining you about the MATLAB symbol. There is plenty of tools in the MATLAB. Okay, not only you can use MATLAB in mechanical engineering, electrical engineering applications. We can also use in biotechnology applications. So one such tool is Symbology. If you also have computational biology tool, bioinformatics toolbox, etc., even in MATLAB, these are the other program tools. I think the participant can mute so that there won't be any disturbance. Now I take you to the MATLAB Symbology alone. There are plenty of tools. One such is Symbology, as I already mentioned. If you see, the Symbology is majorly used for working on modeling, simulating, and analyzing dynamic systems. After the talking, I told you I go for virtual screening and then I go for MD simulation, isn't it? So, and also on yesterday's session, I was explaining you about ADMET properties, LADMET properties. Okay, what are drug likeness properties? What are LADMET? You remember all this? LADMET actually it refers to the pharmacokinetic properties. So whatever properties, pharmacokinetic properties you can predict for a drug in the Swiss ADME or on any other tools and databases, biological databases, okay, that is limited up to determining the properties. But here in this MATLAB Symbology, you can use to construct the models, what happened? You can use to construct the models, pharmacokinetic compartment models. Okay, so in the subsequent slide, you can understand what I mean by pharmacokinetic compartment models. And so this is also used for understanding the pharmacodynamic application. Okay, so you can create models using the symbology and you can go for simulation with that model, whatever you have generated. So for this, you basically you go for using the system pharmacology, especially quantum systems pharmacology. This is a new kind of technology. Okay, this is an emerging kind of a technology found in computational biology applications. So of course, this only MATLAB uses this kind of powerful tool for working on system pharmacology. Okay, it uses generally system biology markup language. Somewhere it is mentioned here. Yeah, system biology markup language. Okay, so actually, there are different areas to work in bioinformatics. One is drug design and vaccine design, and you can the second area I can tell you can work on next generation sequencing. Okay, and the third one, what I can tell you is embedding drug and vaccine design with respect to system biology approach. Okay, this is a third area. System biology is the recent kind of thing user or used by many researchers in the publications. And there is another area of computational biology is synthetic biology, that is designing genetic circuits, and for creating knockout, knock-in genes, transgenics, all these things it utilizes synthetic biology. So in synthetic biology, you use synthetic biology markup language. For system biology, you use system biology markup language. Okay, there is a separate language like HTML to develop these tools. Okay, especially here, if you want to build a compartment models, you can go for this symbology tool. Let me take you to the steps in symbology. There are five major steps in symbology: building tools, simulating tools, estimating parameters, analyzing models, and deploying models. So these are five important things you can find steps in symbology. Steps in symbology, we can build models. So, our course title is related to artificial intelligence and machine learning approaches, isn't it? So one should know even how to create your own tools, okay, and how to work on computational tools if you don't have in vivo facilities in your institute. Okay, if you want to check whether a drug is efficient in treating a disease, what we do, we first go for computational prediction. Okay, a computational prediction of binding affinity of a drug with your particular target receptor, and then we can go for in vitro studies. In vitro studies, I mean, we use T20, T25 flask, and we culture with the cell lines, cancer cell lines, and we can check whether our drug is going to show any anti-cancer effect on the cancer cell and the cell lines. Okay, and the next step, what we do, we go for in vivo studies. We work on some mice model, or we work on animal model like rat or rabbit. Okay, it depends, isn't it? But whatever you work with the mice, ultimately in vivo, what we call as a preclinical trial, the same we can try here in the computation itself to avoid loss of life, not only in phase 1 to phase 4 with respect to humans, to avoid even loss of life even in preclinical trials. Okay, to reduce the loss of life in the mice or rat, what you work. So you can try with this kind of symbology too. So here you're building the compartments, and whatever you simulate is similar to the working on mice model. Got it? So simply you can understand like that. So you can work on pharmacokinetic and pharmacodynamic model. Of course, you are using this kind of a markup language. You create model variants. There are some steps actually. You can find the tutorial point. Yeah. Any doubt you have? You can unmute and answer, question me, because I'm in PPT. And the third step is evaluating the dosing strategies. Okay. So even if you want to estimate how much dose you have to give and how many doses per day, even that can be decided in this sim biology. So because we are doing a kind of a simulation, you can even solve it. Okay, if you using a different algorithms, and you can go for automating the unit conversion. Like if you want to find how much drug you have to feed, like for a mice. Okay, the mice is a small animal when compared to rat. Okay, so what dose you have to give for a mice and what dose you have to give for a rat. Okay, and how about the human? All these things can also be simulated, and even the dose can be fixed accordingly. You can also accelerate simulations through, you can integrate with the supercomputers also. to work on different analysis with MATLAB. So pharmacokinetic model, PK one compartment model. For example, if you want to relieve from pyrogens, that is, if a patient is suffering from fever, and if you want to treat them, generally you provide a drug like acetaminophen, whatever acetaminophen and paracetamol you're going to give, they give in oral route. So oral route, if you give, what is going to happen? Initially, the drug is going to absorb in the blood, isn't it? This is the first step you find in ADMET property. So absorption is going to happen in the blood. So the first best, most important compartment is the blood. So we had only one compartment called blood. But this is for a simple uh, uh, disease. For a simple disease like for treating fever. But if a patient is suffering from liver cancer, okay, then if you consider the blood can be considered as a peripheral component. The major component what we have to target is the liver. So that is a major component, central compartment, and this is the peripheral component. Okay, if you use these two, then you can call that as a two compartment model. And if you're targeting not only the liver, but also you're targeting another organ like pancreas, then also if you consider the blood as one of the peripheral compartment, then you have three compartments. So if three organs are most important in targeting, then you have a three compartment model. Like this, you can have multi-compartment models. Okay, you understand? So we can have as much number of compartments and how much drug is utilized in the blood. For example, if I am taking paracetamol of 500 mg in blood, if it is taking all the 500 mg, but while distributing to a particular tissue, it is distributing only 50%, then only 250 mg is going to distribute. Okay, so and also if you try to find the half-life, how much time it is going to reside in the tissue, that is also most important. You know, drug protein binding. So for this, so what you do, you go for kinetics. You study the kinetics. Not only you study the kinetics during the protein folding, like if you get a structure, protein structure, and if you want to know the stability of your protein structure, what you model, you can also go for folding. Okay, and you can go for energy minimization procedure in that. Now, if you want to determine how much amount of drug is released from blood to tissue to the desired tissue, that is in distribution, you can use the chemical reaction kinetics, CRE. Here in this case, this is a biological reaction engineering. You have certainly a constant called K, rate constant called K distribution. Okay. Likewise, you have K elimination. If unutilized drug, like if only find 50% is distributed, then I'm telling you, only 250 mg is utilized. But not all the 250 is utilized well. Even some unutilized amount will be eliminated in the form of excretion, in the form of urine or any other. Okay, then what is K elimination? How much it is eliminated? Okay, even the rate constant you can find a separate rate constant. So likewise, you can build as many number of compartments. Here, one compartment, how the one compartment reaction looks like, and how the two compartment reaction looks like. So many rate constants kind of come if you go for multiple compartments. So whatever I discussed, okay, so the central compartment, peripheral compartment one, peripheral compartment two, okay, you have that much number of rate constants. As I mentioned, if it is a reversible reaction, you have two types of rate constant, of course. And if whatever I explained you, central, peripheral, dosage levels, okay, all these things, okay, even how much a drug is passed from central to peripheral, and how much drug is passed from peripheral to the second peripheral, and how much it is excreted in the, so all these things we can also able to calculate it using the model analyzer. Okay, so we have to feed some input parameters, and if you go for analyzer, obviously get so for getting an output, you should first feed the parameter values. Okay, even the parameter values like you have to feed, and then you have to click the analyzer. So you can also come to know what is happening with respect to time. I told you, no, even the doses we have how much amount of drug is binding with the protein. Okay, that gives you an idea about how many doses we have to fix per day. Okay, if you see the paracetamol, it resides only 8 hours. But if you see, if a person is suffering from bowels movement, okay, something like diarrhea. If they go for loperamide, then obviously it can, the residence time of the loperamide is around 24 hours. So one person can take one drug a day. Okay, so all these things we can able to simulate with respect to time. Also, we can able to make it out. So for this, you have an option also called run. You can get some information on that. So you can get a nice graph and you get some kind of precision values. All these things are shown in the form of R values. So a kind of bioavailability curves you can find. So this information not only can try with the drugs, but we can also try with the vaccine. Okay, let me show you the software. The MATLAB is an excellent software. Not only for in biology, we have other tools also for biotechnology applications. If you see MATLAB software, you can also find in different certificate courses to get trained. There are so many free certificate courses like how the Coursera, Udemy is going to offer. Similarly, have plenty of courses here in MATLAB. If you are really interested, you can go and you can also learn different courses in the MATLAB. Plenty of tools are available. This is a package, bundled package. Okay, many statisticians use this package for different applications. Now I just opened the MATLAB. Even the MATLAB of I just installed the MATLAB of the latest version R 2024A. Uh, if you don't know anything about MATLAB and if you're very new to the MATLAB, I suggest you to go to the Learn MATLAB. You have an option here. And also, I want to mention that MATLAB uses the command line. Okay, there are different commands like DOS prompt. In MS DOS, if you type the commands, you get a kind of an output, isn't it? Because these commands are already built in the programs to get an output. Similarly, here, even here in MATLAB, you have this command line programming language. If you want to know more about the MATLAB, click Learn MATLAB. Okay, it directs you to the web page. So you can learn through the different courses. If you see, if you want to learn about the Simulink, you can click. You can find 10 courses. If you want to know about the artificial intelligence, machine learning, and deep learning, you have nearly 6 courses. Okay, so 6 courses, major courses. But in the major courses, you have some modules. For example, machine learning on ramp, you have 6 modules. With MATLAB, you have 6 modules. Likewise, deep learning, reinforcement. So one can able to develop the tools, okay, through AI and machine learning, even using the MATLAB. Okay. Now, if you go to the physical modeling, you have something. But what we use more majorly, we can go for general MATLAB. Okay, MATLAB fundamentals, MATLAB programming, object oriented. So these are also out of use. Okay, online training should you can find few more information on this. Okay, so one can able to learn by clicking this learn MATLAB. But if you want to know about some commands, okay, and if you want to know few more information, better go for this request support, okay, or you can go for help. In help, you have examples, you have documentation. If you want to work with an examples, click the examples. You have a detailed explanation in the examples. It tells you, it guides you in each and every step. Okay, you don't need of panicking on this a large package. You have detailed steps mentioned clearly in this MATLAB. Okay, so what you want to work, if you want to work on computational biology, so you can use this. Okay, I think net is too slow. So you have so many. Okay, so uh, yeah. Actually, the net is too slow. So you can able to find some kind of examples. We got it. I think I have selected something else. You are getting few examples here. If you click here, it direct you and it tell you what exactly and how to work on it. So stepwise procedures are clearly illustrated here. And if you want to know what functions they are used and what kind of an apps, all this information also you get in there. Okay. So related to the functions, related to the packages, related to the commands. Okay, all these things are mentioned clearly. So this is like an API. Okay, so detailed documentation you can find here. Okay, So one can learn more about the MATLAB from the examples as well as from the documentation. Even you get much support from the MATLAB. If you face any problems with the installation, or if you want to install uninstall one package and one uninstall one software and want to install two other softwares, everything they can support it. Okay, so the renewal of license is per year. Okay, each and every year you have to renew the license. Okay, so these are some terms of usage of MATLAB. Okay, now let me take you to an example. Okay, so to work on cancer. Okay, I'm going to take you an example, a model to work on cancer. So first I'm going to click open. I have a kind of example. Okay, I'm checking that, not in documents. Then I have to check in C drive. If I install the MATLAB, okay, it is present in program files. MATLAB, I find. Oh, I don't find in MATLAB. Yeah. So then I can go for program files. Still, yes, I got MATLAB. In MATLAB, I have one file in R 2022 examples in biology. I'm still in all files. Data. Yes, this is my model, tumor growth model. Okay, I'm opening a tumor growth model in a MATLAB. So it is opening the same biology model builder. Obviously, there are plenty of tools I told you. So one such tool is the symbology. I'm just opening it. So in this tumor growth work model, we are going to give two different drugs. Okay. I think for a tumor, uh, they use plenty of drugs, isn't it? So here they are showing two different drugs. Okay. Uh, Here you have a central compartment, a peripheral compartment, and if a tumor is growing, okay, in a particular thing, for example, a mice, what is going to happen? So what is the difference between a mice model and rat model? The mice is generally 25 grams to 30 grams. And if you're working on rat, it will be 250 grams to 300 grams. Okay, 10 times the weight. So one should feed the input parameter like body weight. If you're working on human, so what is the weight of the human? So you have to fix that also. Okay, and you have to know what those, for example, if a human is taking a drug, is especially paracetamol, I have mentioned you the 50 kg and below 50 kg they take 500 mg. But if they are kids, they will be taking less than that, 200 mg or 250 mg. So we obviously we fix even the dose, okay, based on the body weight. So all these things also can be feed as the input parameters. So whatever parameters I'm explaining, okay, everything we can feed it here. And whatever compartments you are going to use to check for a disease, you will be feeding here. And the next step is to go for analyzing the model. So after building the compartments and parameters, I just click the analyze. You get this kind of an information now. So paclitaxel generally used for treatment of breast cancer. So this I'm going to check whether how effectively it's going to treat. Okay, so feed some input parameters here. Okay, now I'm going. I've already the model is already developed as an example. So if you want to change the parameters, you can change the parameters in simulation, or else you simply have to click run. Okay, first I clicked analyze. Now I'm going to click run. So generally, if you want to build such a model, initially I showed you 5 important steps, isn't it? You have to learn from the tutorial, and you have to develop a kind of a compartments based on how you want to design. Okay, this is completely based on the research design, how you make, and then you work on it. Okay, viability, efficacy, all these parameters related to pharmacodynamics also we can able to study using this model. So now we got an output for the drug. Okay, so how about the effect with respect to central compartment, and how about the effect with respect to the peripheral compartment? How much time it can, how much this is the time and this is the dosage level. So some information on that you can able to find. Okay, so generally if you want to work on the tumor growth model, you can also work with the same biology concept. Okay, biology tool from the MATLAB. We also have other tools like computational biology for if you go for the next generation sequencing or if you go for uh, the sequence alignment. Okay, we also have a different tools for that to work in MATLAB. So generally, I use MATLAB for system biology approach. This is of course system pharmacology approach. Okay, so the latest publications in reputed journals are uh, worked in worked on system biology. Okay, there are different technical terms, more resembling with each other, but you have. Okay, what is the difference between Autodoc 4 and Pyrex? I mentioned you know the Autodoc 4 is docking a single ligand with the receptor. Autodoc Pyrex is docking multiple ligands or drugs with a single target receptor. Okay. So I think today I have completed how to go for molecular docking analysis using Discovery Studio Visualizer. I showed you hands-on experience. The next I showed you how to work on with MATLAB, especially with SimBiology too. Okay, so this is the completion. And tomorrow I'll be discussing you on virtual screening methods. Okay, virtual screening methods, Autodoc Pyrex. And come across the energy simulation and empty simulation. Okay. Any doubts you can ask me.
Sir, you shows that some
Uh, uh,
poses in
Madam,
the
may I know
start.
your good name?
Myself, Kalpana Pandya, sir.
Oh, good. Glad to talk with you. Now you can ask me, ma'am.
Uh, Sir, you shows that you shows the two ligands with two poses, the same ligand with two poses. So
Mm.
can we dock more than one? Like I tried 5 to 6 ligands with Autodoc, but it doesn't give me the best results. So I tried one by one. So how I learned that method. You are doing the same poses with it.
Mm.
So yes, sir.
Uh, you want, you mean that you have docked four ligands with a receptor, you didn't get any docking result. What do you mean by that? Whether you're not getting any dock score or you're not
Yes, sir.
getting any binding site amino acids after docking.
No dog score and not at all binding subject.
Then,
I generated that, I got that file, docking log file is output,
whether
but it shows heteroatom errors every time.
then I think you are getting trouble with some steps in Autodoc. Okay, so you have to check each and every step carefully. Okay, yesterday I think Director Praveen Ramanujam sir has sent you a video, isn't it? So
Yes, sir.
carefully check and work on each and every step. If you work precisely. Like if I save like protein1.pdb, you should save like protein1.pdb. If I say ligand file as ligand1.pdb, you have to save like that. If I save like pdbqt, you have to save like pdbqt. So everything, even the file name also should be the same. First try exactly, don't deviate even 1% from the protocol what I work. So if only if you practice exactly, then only you can get a kind of an output. You won't get these kind of errors.
Okay,
Okay,
sir.
so
I will
mm,
try. Sir,
yeah.
another thing is, it is a free software, sir. But every time it shows that
What
registration
software
error and the
is
Python error and a directory error, like this error, sir.
is you are you mentioning about Autodoc or you are mentioning about some other tool?
No, sir. I'm only mentioning about Autodoc. I tried Autodoc only. I also work on Mestro, but currently I am trying Autodoc for my docking.
Okay, okay, but you should carefully follow the steps. You should have much patience while working on the first docking. Okay, if you get a result, obviously from the second docking, you will be you can practice very rapidly. Okay, there won't be any problem for you. Only thing is that you have to carefully follow the steps. Okay, and any other doubts from any other participants?
Thank you, sir.
Yeah. Only practice makes perfect. So only the first time practice gives you a better confidence on it. Okay, so slowly you can check and practice. Okay. If no doubts from any other participants, thank you very much for your interactions and patience. So let us see you on tomorrow. Okay. Have a great day to you all. Bye. File format for MATLAB. We have different extensions for MATLAB.